Hello everyone, I'm Alexander Spiridakis, and in this session we will discuss about virtualization challenges and kernel-based virtual machine. So, about virtualization challenges. A good hypervisor, a good virtualization solution, of course, needs to be very efficient. It needs to be tightly close to the near-native performance that the actual host platform offers. The virtualization overhead, although, is a complex thing and it can be quite challenging to reduce. This overhead is mainly having to do with when the guest system tries to access hardware where it shouldn't, or do things that it shouldn't do. The most obvious example is the trap and emulate procedure. Imagine a guest operating system under a hypervisor where it tries to communicate with an emulated device, let's say a network controller. Upon this instruction, writing, for example, to a memory segment to write a packet to the network controller, the hypervisor immediately has to pause the guest execution. This is because you abstract the hardware. The guest doesn't know that there is a real network interface, and you don't certainly want your guest to fiddle or meddle with that network controller because other guests would like to do so as well. So instead, hypervisor pauses the guest execution and then emulates the device behavior. For example, if the guest writes to a memory segment of the device, this is replicated, the behavior is emulated, and then we get back the final result. After this, the guest is resumed. Of course, in the meantime, we lost major cycles, CPU cycles, in actually emulating the device, where we could have spent it in actually doing the work that we needed to. So this cycle is repeating over and over again. The never-ending cycle of virtualization is guest tries to do something, hypervisor traps and pauses the guest, emulates the behavior, then resumes. Of course, this is very costly. More complex emulation devices equals larger virtualization overhead. And in the end, all that matters in virtualization is I/O performance. And I say this because almost all hypervisors manage to offer performance that is near native for CPU and memory workloads. But input-output such as storage devices and network controllers is the most important challenge in virtualization. This is an example for I/O performance. This graph here shows a network interface and how much throughput it can achieve. The first bar is on an emulated environment, basically trying to emulate the same exact network controller, while the second bar is the actual performance of the network controller in a host, the real network controller. As you can see here, the emulation only can offer 2 megabits per second, while the host can almost reach the 100 megabps throughput of the controller. Of course, this is an extreme example where the emulation of the network controller is not as efficient as it could be, but we see that the performance is much worse because there are far too many virtual machine exits. Basically, the guest, whenever tries to send a packet, it has to be paused by the hypervisor, emulate the network controller, and then get back to processing. So we lose valuable CPU cycles for the actual emulation instead for the I/O requests. So, having said that and seeing the actual problem of emulation, there are other techniques, of course, like para-virtualization, hardware-assisted virtualization, and all these concepts can be seen being used in a specific hypervisor, a very well-known hypervisor, which is KVM, or Kernel-based Virtual Machine. So KVM is into upstream Linux kernel since version 2.6. It's a full virtualization solution, but it uses multiple approaches. It combines emulation, not by itself, as we will discuss later, para-virtualization and hardware-assisted virtualization for all types of workloads. The interesting point, and its differentiating factor from other hypervisor, It's that it literally transforms the Linux kernel into a full-blown hypervisor. The issue here is that hypervisors are very complex software. In the end, a hypervisor is a small operating system which manages resources, memory, tries to do the resource allocation, many complex stuff which are already covered by operating systems. So instead of KVM re-implementing all those features, it tries to utilize the whole Linux kernel, its well-tried and tested infrastructure, for this purpose. Among its features is support for hardware virtualization. It's high performant for the targets that it's supported and scalable. Of course, there is a huge ecosystem around it, mainly revolving about open source. Many types of virtualization, mainly having to do with CPU and memory, of course, as we will see later the details, and it almost exclusively used in conjunction with user space tools. Remember that KVM sits on the kernel side, but by itself it doesn't really do much, meaning that it's responsible for creating VMs, running the native execution of the guest operating system into the host processor, managing the memory, but that's it. In order to have a whole system, we need to rely on a user space tool, such as KEMU or KVM tool. These tools basically implement a whole system. They emulate a whole machine model, as we say, being it a specific Intel machine model or an ARM one. But this machine model includes peripheral devices, the memory layout, and these sort of things. So in this picture here we can see the overall Linux KVM architecture together with KEMU, of course. So if you look at the picture, we see this is our hardware resources, our CPU, memory, and I/O devices, and then on top of them sits the whole Linux kernel with its drivers talking directly to the hardware. Then a little part of it inside the kernel is what is called KVM, and it offers an interface to user space applications. The gray box and up from there is a user space application. It offers capabilities to user space applications to create virtual machines, accelerated virtual machines though, not entirely emulated. The CPU and memory components are fully virtualized. The machine model is actually emulated by KEMU, as we will show in the next slide. So in this slide, in this picture, we see the KVM-QEMU interactions, how they interact with each other. So first, KEMU will ask for KVM to create a virtual machine, after of course allocating its own memory and starting itself. Then KVM will handle all the initialization stuff that is needed for hardware-assisted virtualization. Let's say set up the memory, the page tables, be able to run native CPU instructions on the host processor, create the vCPUs, and finally jump to guest code. At some point the guest will run normal arithmetic operations, let's say, adding, subtracting, multiplying, and at some point it will request an I/O. For example, write a letter to a serial device, use a timer, send a packet to a network controller. At this point, the hypervisor will trap, because KVM does not emulate devices. The user space application does this, the hypervisor, the KEMU instance. So the hypervisor will pause the guest, will have a world switch or a context switch. We will interrupt the guest. We will handle the exit, see why we exited from the guest, what instruction caused the exit. Was it prefetch abort? Maybe something went wrong. Was it an memory mapped I/O? Maybe we need to emulate that. So the user space emulates the memory mapped input-output and then finally returns back to the guest. So this is a never-ending cycle of trap and emulate, where the hypervisor tries to make use of the hardware-assisted virtualization for CPU and memory-bound workloads, and then relies on emulation for other peripherals that are not included in KVM. Of course, KVM initially started as an x86 only project. It was introduced at version 2.6 only for x86 at the time. But since then, a lot of other architectures have been ported with KVM. So initially, the ARM architecture didn't support virtualization features at all. So in order to virtualize ARM software, you would have, and operating systems, you would have to rely on para-virtualization and emulation, which can be slow or inefficient depending on the use case. But with later architectures for ARM v7a and beyond, especially with the introduced Cortex-A15 processor, specific hardware virtualization extensions were made into the hardware in order to make hypervisors more efficient in the ARM architecture. Later, ARM v8 came into the picture, where it focused the architecture to 64 bits. It's a relatively new introduction and change. The good thing is that it's backwards compatible, and it offers many virtualization features. Actually, it's quite more better than ARM v7. And KVM on ARM is supported in upstream Linux since version 3.9. The features that the KVM on ARM supports is mainly CPU and memory virtualization, along with features for interrupts and timers. It's important to note here that when we say KVM on ARM, someone thinks, why would you need virtualization on embedded devices? But the important thing to note is that with the movement to ARM v8 and 64 bits, the ARM ecosystem is starting to move into the server market, where virtualization is, of course, the #1 reason. If you don't support virtualization for server products, you can't do anything. So it's a very interesting movement where we will see micro low-power servers to compete with the powerhouses from Intel. It will be a very interesting future. As a last thing, in what we do in Dreams and to expose a little bit more in our activities, beyond KVM, we also have the concept of a real-time operating system or a general-purpose operating system coexisting in the same system on chip. So why is this different from KVM? KVM is a complex software, of course. It relies on Linux. It has some issues with real-time guarantees in that it's not preemptive. There are some patches and some work trying to make KVM be true real-time, hard real-time, but it's an ongoing process. So in mixed criticality systems, where we have different criticality levels according to the software that we need to run, for example, let's look at an automotive example, where you have your in-vehicle infotainment system, which you normally would run Linux on it, but maybe some cluster meters about your tachometer, your speed, your fuel gauge. All these things are more safety critical related, so you would not want Linux to interact with these things. So you need a separation layer, and someone could say that, okay, virtualization does this very well. You could use KVM to start a real-time operating system for the safety critical part and a general purpose operating system for the infotainment. The problem is that KVM might not be hard real-time for every task, maybe have larger latency than needed. So instead of using virtualization, which is a complex concept, we rely on specific extensions in the ARM hardware. In this instance, we split the CPU world in two segments. The secure one, showing in this picture here, called trust zone, and the non-secure one. So without a virtualization layer, but only a monitor firmware layer, which is a very thin layer that basically just do the context switch that might be needed between the two different worlds. On one side we have our real-time operating system, and on the other side we have regular Linux with KVM virtualization features intact, and when the user wants, he can utilize multiple VMs. So what this offers is that your real-time operating system runs natively. There's no virtualization layer. the same applies for Linux. You split the resources apart through the monitor layer of infrastructure, and each world speaks to their own peripheral devices, completely isolated without having to interact with the other world. So by this implementation we get best of both worlds. We have very low latency for the real-time operating system. We get all the nice feature-rich multimedia features in Linux, plus on top KVM on ARM virtualization. And you have your criticality levels completely isolated, the safety critical from the infotainment system. And this is the concept that we are working on, and we are hoping that as the time passes by, we'll have a more concrete implementation. So that is all for the small introduction to virtualization challenges and KVM. Thank you for your attention.